Industry. It is capable to generate AC power at a specified frequency. It is also called a synchronous generator. Electricity is produced in alternators by electromagnetic induction. To generate electricity in a coil, either the coil should rotate with respect to magnetic field, or a magnetic field should rotate with respect to the coil. In the case of alternator, the latter approach is used. Rotor and armature coils are the two main parts of an alternator. Rotor produces a rotating magnetic flux. Armature coils are stationary. And rotating magnetic flux associated with the rotor induces electricity in the armature coils. This kind of rotor shown here is known as salient pole rotor. For gaining better insight of its working, let's consider a rotor with just 4 poles. Rotor coils are excited with a DC power source. Magnetic field produced around it would be as shown. The rotor is made to rotate by a prime mover. This makes the rotor flux also rotate along with it at the same speed. Such revolving magnetic flux now intersects armature coils, which is fitted around the rotor. This will generate an alternating EMF across the winding. Here is a slowed-down version of rotor-stator interaction. For this 4-pole system, when the rotor turns half revolution, induced EMF takes 1 complete cycle. It can be easily established that frequency of induced EMF, rotor speed, and number of poles are connected through following relationship. It is clear that frequency of electricity produced is synchronized with mechanical rotational speed. For producing 3-phase AC current, 2 more such armature coils, which are in 120-degree phase difference with the first, is put into the stator winding. Generally, one end of these 3 coils are star-connected, and 3-phase electricity is drawn from the other ends. It is clear from this equation that in order to produce 60 Hz electricity, a 4-pole rotor should run at following RPM. Such huge RPM will induce a tremendous centrifugal force on poles of the rotor, and it may fail mechanically over time. So salient pole rotors are generally having 10 to 20 poles, which demands lower RPM. Or salient pole rotors are used when the prime mover rotates at relatively lower RPM. Pole core is used to effectively transfer magnetic flux, and they are made with fairly thick steel lamina. Such insulated lamina reduces energy loss due to eddy current formation. Armature winding of 3-phase 12-pole system is shown here. A stator core is used to enhance magnetic flux transfer. DC current is supplied to rotor via a pair of slip rings. DC current is supplied either from an external source or from a small DC generator, which is fitted on the same prime mover. Such alternators are called self-excited. With variation of load, generator terminal output voltage will vary. It is desired to keep the terminal voltage in a specified limit. An automatic voltage regulator helps in achieving this. Voltage regulation can be easily achieved by controlling the field current. If terminal voltage is below the desired limit, AVR increases the field current, thus the field strength. This will result in increase in terminal voltage. If terminal voltage is high, the reverse is done. Hope you had a nice introduction to working of alternators. Thank you.
Wired to a home's electrical system, a standby generator automatically powers up in the event of an outage. Production starts with the stator. It's the stationary core of the alternator, the part that converts energy from the motor to electricity. A press compacts 100 or more laminated steel discs to create the stator core. Machinery lifts the stator core out of the assembly device and transfers it to the next station. Here, an automated system insulates the numerous slots in the core. Meanwhile, at another station, an automated system winds copper wire onto a mandrel. This configures the copper windings to fit the core slots. Once all the windings have been correctly arranged on the threading tool, the technician is ready to transfer them to the stator core. He places the stator on top of the threading tool and activates a hydraulic device that pushes the wires up through the tool and into the slots of the stator core. Then it's into the lacing machine. This machine crochets a string wrap around the bundles to hold the wires together. With the wiring precisely wound and wrapped, this important generator component is ready for the finishing touch, a clear varnish. To produce the alternator's rotating part, the rotor, the technician stacks laminated steel discs to the same height as the stator core. He lubricates the opening in the center of the discs. He inserts a shaft, and a press pushes it into the stack to complete the installation. Then it's over to an automated welder. The machine grips the rotor at both ends and slowly turns it, as a robot welds both caps to the rotor body. The technician unclamps the rotor from the welding machine, and then tucks insulation into slots on the sides. The rotor then goes for a spin in a machine that winds bands of copper wire around the insulated sections. These wires will act as electromagnets and help produce electrical current. They're now ready to assemble the standby generator. Using a lift, the technician lowers the engine into position. He joins the rotor shaft to the engine crankshaft. Next up is the stator. The technician slides the stator onto the rotor. He anchors the stator and rotor to the generator base. He attaches a motorized carbon brush to copper rings on the rotor shaft. The brush will collect electricity from the shaft and transfer it to the generator controller. He secures it to the end bracket with screws. He connects the wiring harness that moves electricity from the brush to the controller. He links the other end of the harness to the engine. He plugs in a sensor to monitor oil pressure and makes all the other electrical connections. The assembly of this standby generator is complete.